Fine. Let's start. Number 10. UY Scuti. There's a star sitting about 5,100 light-years away, in a dim little constellation called Scutum that you have almost certainly seen in a video before. You just didn't know its name. It's the one at the end of those size comparison clips. The ones that start with Earth as a single pixel next to the Sun, and then keep zooming out, and out, until the Sun itself becomes the pixel. And this enormous, sullen red thing fills the entire screen while dramatic music plays. That thing is UY Scuti, and for years it wore the crown, the biggest star we knew of. Not the heaviest, not the brightest, the widest, the largest single sphere of anything humans had ever pointed a telescope at. Here's how big we're talking. Take UY Scuti and drop it right where the Sun is. Delete the Sun, put this in its place. Mercury is gone. Vaporized, deep inside the star. Venus, gone. Earth, gone. Mars, gone. On the more conservative modern estimate, the surface of this star reaches out past the orbit of Mars. On the older estimate, it pushes all the way out toward the asteroid belt. Everything you think of as the inner solar system, the entire neighborhood where all the action happens, all of it would be inside the star. You would be inside the star. If you could somehow fly a plane around its equator at the speed of a commercial jet, it would take you thousands of years to make one lap. The Sun already dwarfs us to the point of absurdity, and you could line up around 1,000 suns across the width of this thing. Now, the official explanation is straightforward enough. UY Scuti is a red supergiant. It's an old, dying star that has swollen up as it burns through the last of its fuel, its outer layers puffing out into this vast, cool, tenuous shell. Cool is relative, of course. Its surface is thousands of degrees. But compared to the blue-white fury of a young star, it's cool, and that's why it glows that deep, brooding red. But here's the thing. We're not actually sure how big it is. And I don't mean we're off by a rounding error. I mean that between two different measurements, the estimated radius of this star got cut nearly in half. One method, using an older interferometry technique, put it at around 1,700 times the radius of the Sun. Then, a newer analysis, using a better distance from the Gaia spacecraft, brought it down to around 900. That's not a small correction. That's the difference between a star that reaches the asteroid belt and one that stops at Mars. That's an entire solar system's worth of uncertainty. Think about what that actually means. This is one of the most famous stars in popular astronomy. It is starred in 100 viral videos as the ultimate example of cosmic scale. And when you ask the simple question, how big is it? The honest answer is a shrug, and a range you could park several planets inside of. The problem is that stars like this don't have edges. Not really. There's no hard surface where the star stops and space begins. The outer atmosphere just gets thinner and fades away, pulsing and shuddering as the star breathes. Ask where the edge is, and you might as well ask where a fog bank ends. So we argue about it. We refine the number. And the biggest, most iconic star we know is also, quietly, one of the ones we can measure the least confidently. That's a strange thing to sit with. The bigger something gets out here, the harder it becomes to even say where it ends. Number 9. VY Canis Majoris. So if UY Scuti is the star we can't quite measure, this next one is the star that won't hold still long enough to be measured, because it's falling apart. VY Canis Majoris, it sits about 3,800 light-years away in the constellation of the Great Dog, the same patch of sky that holds Sirius, the brightest star in our night. And it is a red hypergiant, which is the tier above supergiant, the rank we reserve for the truly ridiculous. Estimates put its radius at around 1,400 times that of the Sun, and some measurements have pushed that figure even higher, up toward 2000. Let me ground that for you. If UY Scuti reaches out toward the asteroid belt, VY Canis Majoris reaches further. Drop it where the sun is, and its surface would swallow the orbit of Jupiter. On the higher estimates, it stretches out toward Saturn. There is a real, serious astronomical measurement in which a single star is the size of the orbit of Saturn. You could fit somewhere around 7 quadrillion Earths inside its volume. That's a 7 with 15 zeros after it. The number stops meaning anything. Your brain just files it under a lot and moves on, because it has to. But the size isn't even the unsettling part. The unsettling part is what it's doing. VY Canis Majoris is dying, loudly. It is throwing itself into space. Every single year, it sheds an amount of material equal to about 30 times the mass of the entire Earth. Not over its lifetime. Every year. 30 Earths blown off the surface as dust and gas, year after year after year. It has already lost more than half of everything it started with. Around this dying star, there is now a chaotic, glowing cloud of its own ejected guts. And when astronomers used Hubble to look closely, they could trace the individual outbursts, like layers in a tree stump, going back roughly 1,000 years. Now, the textbook answer is that massive, dying stars lose mass. We know this. It's expected. Big stars have powerful stellar winds, and near the end, they get unstable and puff material off. Fine. But here's the thing. The way VY Canis Majoris is doing it doesn't match the calm, steady wind we'd expect. When Roberta Humphreys and her team studied those ejections, they found huge, discrete, lumpy plumes. Arcs and knots and clumps of material, flung out in specific directions, at specific times, like the star is convulsing. Something inside it is heaving. Great surges of energy are rising up from the interior and blasting chunks of the star clean off, and we don't fully understand the mechanism driving it. So picture it. The largest kind of star there is, so big it would engulf the outer planets, and it's not sitting there serenely. It's shuddering. It's tearing pieces off itself and hurling them into the dark. In fits and spasms we can see but can't quite explain. And every one of those spasms might be a rehearsal for the final one, the day it collapses and detonates as a supernova. It's enormous. And it's frightened, if a star can be frightened. It's coming apart at the seams, one continent-sized plume at a time. Number 8. R136A1. Alright, so far, big has meant wide. Stars so swollen they'd swallow planets. But there's another way to be big, and it's arguably more terrifying, because it's the one that packs a punch. This next object isn't the widest star. Not even close. It's the heaviest. R136A1. The name sounds like a serial number, and honestly it basically is, because it lives in a crowd so dense that astronomers had to catalog it like an item in a warehouse. It sits in a place called R136, which is a tight, brilliant cluster of young stars at the very heart of the Tarantula Nebula, in the Large Magellanic Cloud, a small galaxy orbiting our own about 160,000 light-years away. And R136A1 is the most massive star we have ever found. The current best estimate from a 2022 study using a sharp new image from the Gemini South Telescope puts it at around 196 times the mass of the Sun. That figure comes with a range, somewhere between about 170 and 230 solar masses. But the headline stands. Nearly 200 suns worth of material, compressed into a single star. Now, that 2022 number is actually a downgrade. Earlier estimates had suggested this star might be 250, even 300 solar masses. What happened is that the newer, sharper image managed to separate R136A1 from a few close companions that had been blurring together with it. Some of that mass belonged to its neighbors. But even after the correction, even after being humbled a little, it's still the champion. Still the heaviest star known to exist. And unlike the cool, red, bloated giants we just met, this one is the opposite in every way. It is young. It is small, relatively speaking, only about 40 times the sun's radius, which for this list makes it practically a marble. And it is savagely, blindingly hot. It burns blue-white, and it pours out several million times more light than the sun. If you swapped it for the sun, the Earth would be sterilized in moments. It is a floodlight the size of a small star and the temperament of a bomb. Here's the thing, though. A star this massive is living on borrowed time, and it knows it. The more mass a star has, the faster and more violently it burns through its fuel. Our sun will live for around 10 billion years, sedate and stable. R136A1 will live for maybe a few million. That's it. In cosmic terms, it's a mayfly. It flares into existence, burns with the fury of millions of suns, sheds staggering amounts of mass in a ferocious wind, and then dies, probably in a spectacular collapse, all in the time it takes a slower star to barely clear its throat. That's the trade. To be the heaviest, you agree to burn out almost immediately. This star is the brightest, most massive thing of its kind we've ever cataloged, and it's already sprinting toward its own funeral. It doesn't get to be old. Nothing that burns this hard does. Number 7. The Carina Nebula. Let's pull back. Way back. Because so far we've been looking at individual stars. Single points of light, however monstrous. But stars don't come from nowhere. They condense out of vast clouds of gas and dust. And some of those clouds are so large, they make even a hypergiant look like a spark struck in a cathedral. The Carina Nebula, about 7,500 light-years away, hanging in the southern sky where most of us in the north never get to see it properly. And it is a stellar nursery, one of the largest and most active in this whole region of the galaxy. Depending on where you draw its edges, it stretches somewhere between 200 and 460 light-years across. Sit with that for a second. Light-years. The whole star, UY Scuti, the one that would swallow the inner planets, is measured in a few light-minutes across. This cloud is measured in hundreds of light-years. If UY Scuti were a grain of sand, the Carina Nebula would be a coastline. You've probably seen a piece of it, even if you don't know the name. When the James Webb Telescope released its first images in 2022, one of them was a landscape that looked like a mountain range at dusk, golden peaks and valleys glowing under a haze of blue, with tiny points of light scattered above like stars over a canyon. They called it the Cosmic Cliffs. That's Carina. That mountain range is a wall of gas and dust light, years tall, being slowly eaten away by the radiation of newborn stars just out of frame. It's 4 times the size of the more famous Orion Nebula, and actually brighter. The only reason it isn't as famous is a quirk of geography. It's too far south for most of the world's big historical observatories to have made it a poster child. If it hung where Orion hangs, in a spot everyone could see, it would dominate our idea of what a nebula looks like. But here's the thing about Carina. It is not a peaceful place. We tend to think of a nursery as gentle. This one isn't. Because tucked inside it is a star called Eta Carinae, and Eta Carinae is a monster in the final unstable chapter of its life. In the 1840s, it did something extraordinary. It brightened until it was one of the brightest stars in the entire night sky, blasting off enough material to form a small nebula all its own, and then it faded back down. It survived, but it's still there, still churning, still primed, and one day, maybe soon in cosmic terms, maybe tonight, it will go supernova. So the Carina Nebula is both things at once. It's a place where stars are being born, condensing out of the dark, igniting for the first time. And it's a place where a giant is dying, waiting to detonate and blow a hole through the very cloud that's making new suns a few light years over. A nursery and a graveyard, sharing the same enormous room. Everything out here is like that if you look long enough. Creation and destruction don't take turns. They happen in the same place, at the same time, on a scale that makes the words themselves feel too small. Number 6. NGC 6872. Okay, we've done stars. We've done a cloud that builds stars. Now we take the step that really breaks people, because it's the step where the numbers stop being planets and start being galaxies. Our galaxy, the Milky Way, is around 100,000 light years across. Maybe a bit more if you're generous about the edges. It holds a few 100 billion stars, arranged in those beautiful spiral arms, and it is, by any human standard, unimaginably large. Light, the fastest thing there is, takes 100,000 years just to cross it. When you look up at the band of the Milky Way on a dark night, you are seeing the inside of a structure so vast that our entire recorded history is a rounding error against the time it takes light to traverse it. Now meet NGC 6872. It's a spiral galaxy, same basic type as ours, sitting about 212 million light years away in the southern constellation of Pavo, the Peacock. And it is the largest spiral galaxy we know of. It stretches about 522,000 light years from the tip of one arm to the tip of the other. More than 5 times the width of the Milky Way. Not 5 times the stars, not 5 times the mass. 5 times across. If you replaced our galaxy with this one, its arms would reach out well past our nearest galactic neighbors. It's so big that in 2013, a team working with archival ultraviolet data from the Galax Space Telescope had to formally crown it the largest known spiral, because nothing else came close. They sometimes call it the Condor Galaxy, because of the way its arms spread out like enormous wings. And when you see it, those arms look wrong, stretched, drawn out too far, too thin, like taffy that's been pulled, which is exactly what happened. Because here's the thing, NGC 6872 didn't grow this big on its own. It has a companion, a much smaller galaxy called IC 4970, only about a fifth of its mass, and the two of them have been locked in a slow gravitational encounter. As the little one swept past, its gravity grabbed the arms of the big spiral and hauled them outward, stretching them to this absurd, record-breaking span. Which means the record is temporary. That's the twist. This is not a galaxy that is intrinsically, permanently the biggest. It's a galaxy caught in a moment. The tidal forces of a near collision have pulled it into this extreme shape, and over hundreds of millions of years, the physics may reverse. Some of that drawn-out material might even collapse and gather into a whole new small galaxy at the end of one arm, and NGC 6872 itself may settle back down, smaller, more ordinary. We are looking at a giant that is only a giant right now. Catch it in a few 100 million years, and the title might belong to something else. Out here, even the record holders are just passing through a phase. The universe doesn't do permanent. It does moments that happen to last longer than we do. Number 5. IC 1101. So NGC 6872 is the biggest spiral, a stretched out pinwheel, 5 Milky Ways wide. Hold on to that number, 5, because we're about to make it look quaint. IC 1101. It sits roughly 1 billion light years away, enthroned at the very center of a huge cluster of galaxies called Abell 2029. And it is not a spiral. It's an elliptical, which means it has no graceful arms, no disk, no structure you'd recognize from a poster. It's just a vast, smooth, glowing swarm. Imagine a ball of stars that fades softly at the edges, with no clear boundary, holding an amount of light that doesn't seem like it should come from one object. The size of IC 1101 is genuinely hard to state, and I want to be honest about why. Because it matters. Depending on how you measure it, where you decide the galaxy stops, you get numbers ranging from around 600,000 light years across. On the conservative end, up to several million light years if you include its faint outer halo, the ghostly extended glow of stars around it. Even the low estimate makes it several times the size of NGC 6872. The high estimate makes it monstrous beyond comparison. And the stars. The Milky Way has a few hundred billion stars. IC 1101 is estimated to hold something on the order of 100 trillion. Trillion. That's not a typo, and it's not a small jump. For every single star in our galaxy, this one may hold a few hundred. If you could stand on a world somewhere inside it and look up, the night sky might not be black at all. It might be a wash of light, so crowded with stars that true darkness never falls. Here's the comparison people always reach for, and it's the right one. If you took IC 1101 and placed it where our own galaxy sits, its edge would engulf the Andromeda Galaxy. It would swallow Triangulum, the Magellanic Clouds, and everything in between. Our entire local group, the collection of galaxies our Milky Way belongs to, our whole cosmic address, would fit inside this one object with room to spare. But here's the thing you have to understand about IC 1101. It didn't grow this big by being peaceful. It grew this big by eating. Giant galaxies at the hearts of clusters become giant through cannibalism. They sit at the gravitational bottom of the cluster, the lowest point. And over billions of years, other galaxies fall toward them. Sink in. Get torn apart and absorbed. Every one of those 100 trillion stars represents a smaller galaxy's worth of material that wandered too close and never left. IC 1101 is a graveyard of galaxies that used to be independent, used to have their own names, their own shapes, their own histories. All of it now dissolved into one enormous, featureless glow. And it's probably still doing it. Still sitting there at the center of its cluster, patient, its gravity a slow drain that everything nearby is circling. It didn't win the title of one of the largest galaxies by being the best. It won it by outlasting and consuming everything around it. That's a different kind of big. Not born big. Grew big by devouring. The largest things in the universe are often just the ones that ate the most. Number 4, Alcyonius. Right. So a galaxy can hold 100 trillion stars and swallow its entire neighborhood. Surely that's the ceiling for a single object. Surely nothing that counts as one galaxy can be bigger than that. Let me introduce you to Alcyonius. It was found in 2022, hiding in data from a radio telescope network called LOFAR, spread across Europe. A team led by an astronomer named Martijn Owe at Leiden University was hunting through the radio sky, and they found something that stopped them cold. A single galaxy, one object, stretching at least 16.3 million light-years from end to end. Let me say that number again, slowly, because it's easy to let it slide past. 16 million light-years. IC 1101, the galaxy that could swallow our entire local group, is at most 6 million light-years across on its most generous measurement. Alcyonius is nearly 3 times longer than that. It is roughly 100 times the length of the Milky Way. It is a single galaxy that is longer than most clusters of galaxies. If you put it in our neighborhood, it wouldn't just engulf the local group. It would stretch far out toward other groups of galaxies entirely, a bridge of one object spanning distances we normally reserve for the gaps between whole galactic communities. Now, I need to be honest with you about what's actually so big here, because it's the key to the whole thing. Most of Alcyonius is not stars. The galaxy at the center, the part made of suns and planets and ordinary matter, is fairly modest. It's a normal elliptical galaxy, total mass around 240 billion suns, with a central black hole of a few hundred million solar masses. By the standards of this list, that's unremarkable. Average, even. What makes Alcyonius a record breaker is what's pouring out of it. 2 enormous jets of plasma, blasting from the black hole at its core, feeding two colossal lobes of glowing, magnetized gas that balloon out into intergalactic space in opposite directions. Those lobes are the 16 million light years. Vast, tenuous, invisible to normal telescopes, but blazing in radio waves. The galaxy is small. Its exhaust is the biggest single thing we've ever found. And here's the thing that genuinely bothers astronomers. Nobody knows why it's this big. Because the host galaxy is so ordinary. There are far bigger galaxies out there, with far more massive black holes, pumping out far more energy, and their jets don't reach anything like this size. So why did this average, forgettable elliptical grow the largest structure of any single galaxy in the known universe? Maybe it sits in an unusually empty patch of space, so its jets met no resistance and just kept going. Maybe there's something special about the environment, the density, the magnetic fields. Maybe we caught it at a rare moment. But the honest answer, right now, is that we don't fully know. An unremarkable galaxy did something no giant could. It reached across 16 million light years of nothing, quietly, in a part of the spectrum our eyes can't see, and became the largest single object of its kind. And when we ask it how, or why, it doesn't answer. It just keeps blowing those two vast bubbles into the dark, for reasons entirely its own. Number 3, the Abell 1201 black hole. We've been going bigger and bigger, wider and wider. So now I'm going to do the opposite. I'm going to show you an object that is, in a sense, a single point. And it might be the most staggering thing on this entire list, because all of its size is hidden inside its weight. In 2023, a team of astronomers at Durham University, led by James Nightingale, announced the discovery of a black hole at the center of a giant galaxy in a cluster called Abell 1201, sitting about 2.7 billion light-years away. And this black hole has a mass of around 33 billion times the mass of the Sun. 33 billion suns, compressed into a single point of gravity so complete that not even light escapes it. Let me try to make that real, because black hole masses are slippery. The black hole at the center of our own Milky Way, Sagittarius A star, is about 4 million solar masses. This one is more than 8,000 times heavier than that. The famous black hole that we photographed, the one in the galaxy M87 that made headlines as the first ever image of a black hole, that one is about 6.5 billion solar masses. This is 5 times bigger than that. We are talking about an object near the theoretical upper limit of how large a black hole is even thought to be able to grow. The event horizon, the point of no return, the actual edge of this thing, would be so vast that our entire solar system, the Sun, and all the planets and the distant comets would fit inside it many, many times over. It is a hole in space wider than the orbits of everything we call home, and it is heavier than a small galaxy, and it is utterly, perfectly dark. Now here's the part that I find almost more incredible than the size. How did they even find it? Because a black hole like this isn't feeding dramatically. It's not blazing with light. It's dormant, silent, invisible. You can't just take a picture of it. So the Durham team did something clever. They used gravitational lensing. This monster's gravity is so intense that it bends the light of a more distant galaxy passing behind it, warping and smearing that background light into arcs. And by measuring exactly how that light was bent, and running hundreds of thousands of simulations on a supercomputer to match the pattern, they could weigh the invisible thing doing the bending. It was the first time a black hole had ever been discovered this way, purely by its shadow on the light of the universe behind it. They never saw the black hole. They saw what its gravity did to everything else and worked backward. And that should unsettle you a little, because it means there are almost certainly more of these out there. Silent, dormant, ultra-massive black holes sitting at the hearts of distant galaxies, not glowing, not announcing themselves, just quietly bending the cosmos around them. We can only find them when the geometry lines up just right, when there happens to be a bright galaxy behind them for their gravity to distort. The ones without a convenient backlight stay hidden. Invisible giants, heavier than galaxies, scattered through the dark, and we can only catch the ones that happen to be standing in front of a light. The biggest things aren't always the ones you can see. Sometimes the biggest thing in a galaxy is the one part of it that gives off nothing at all. Number 2, El Gordo. So we've climbed from stars, to nebulae, to galaxies, to the monster black hole hidden inside one. Now we go up one more level, to a structure so large it contains thousands of galaxies at once, and not just any structure, the heaviest distant one we've ever weighed. Its formal name is a string of letters and numbers, ACTCL J01024915, but the astronomers who found it gave it a better one. They called it El Gordo, Spanish for the fat one, and it earned the nickname. El Gordo is a galaxy cluster, sitting about 7 billion light-years away in the southern constellation of Phoenix. And when I say galaxy cluster, I want you to hear that properly. It is not a galaxy. It is a collection of hundreds upon hundreds of galaxies, each one holding its own hundreds of billions of stars, all bound together by gravity into a single titanic structure. And the total mass of El Gordo is somewhere between 2 and 3 quadrillion times the mass of the Sun. A quadrillion is 1,000 trillion. So we're talking about, at the high end, 3,000 trillion suns worth of matter in one gravitationally bound object. It is the most massive galaxy cluster known at its enormous distance or beyond. Because it's 7 billion light-years away, we're seeing it as it was 7 billion years ago, when the universe was only about half its current age. This is a giant from the deep past, and it was already this colossal when the Earth didn't even exist yet. But El Gordo isn't just big, it's violent, because it isn't one cluster. It's 2, caught in the act of colliding. 2 massive galaxy clusters, falling into each other at speeds of several million kilometers per hour. And when clusters collide, something strange and beautiful happens. The galaxies themselves, being mostly empty space, mostly pass right through one another, like 2 swarms of bees crossing paths. But the hot gas that fills the space between the galaxies, that doesn't pass through, it slams together, heats up, and glows in X-rays. And the dark matter, the invisible scaffolding that makes up most of the cluster's mass, sails ahead, separating from the gas it left behind. So when we map El Gordo, we can actually see the collision frozen in progress. The galaxies and dark matter pulled out ahead, the hot gas dragging behind, stretched into a shape that gave the whole thing the look of a cosmic comet. Now here's the thing that makes El Gordo more than just a pretty pileup. It might be a problem. Because a structure this massive, existing this early in the history of the universe, is hard to explain. Our best models of how the cosmos assembles structure, how gravity slowly pulls matter together into ever larger clumps over billions of years, those models have a rough schedule. And a 2 to 3 quadrillion solar mass cluster, fully formed and violently colliding when the universe was half its current age, sits right at the edge of what that schedule allows. Some researchers have pointed at El Gordo and asked, quietly, whether it should even be there. Whether something in our understanding of how fast the universe builds things is incomplete. The debate isn't settled. The mass estimates have wobbled, drifting down from 3 quadrillion toward 2 as the measurements improved, and the tension may yet dissolve. But that's the unsettling shape of it. We found the fattest, most violent cluster in the distant universe, and part of the scientific community looked at it and wondered if it was too much, too soon. A giant so large it doesn't just break your sense of scale. It might bend the timeline. Number 1. the huge, large quasar group. We've reached the top, and I want to be honest with you before we start. Everything up to this point, however enormous, was still a thing. A star, a cloud, a galaxy, a cluster. Objects you could, in principle, point at. This last one is bigger than all of them combined, by a margin that makes the word bigger feel broken. And it may be the single most philosophically disturbing structure we have ever found. Not because of what it's made of, because of what its existence might mean. In January of 2013, a team led by an astronomer named Roger Close at the University of Central Lancashire announced that they had found the largest structure in the known universe. They called it the Huge, Large Quasar Group, the Huge LQG, and the name, for once, is not an exaggeration. Here's what it is. A quasar is the blazing core of a young galaxy, a supermassive black hole in the middle of feeding so ferociously that it outshines all the stars around it. Quasars are among the brightest single objects in the entire cosmos. The Huge LQG is a group of 73 of these quasars, 73 galactic cores, strung together across space in one associated structure. And the size of that structure is where language gives up. It spans around 4 billion light years across its longest axis. Let me try, and I'll probably fail, to make you feel that. The observable universe is about 93 billion light years across in total. This one structure spans 4 billion light years of it. It would take light itself, moving at the ultimate speed limit of reality, 4 billion years to travel from one end of this thing to the other. That's nearly a third of the entire age of the universe, just across one structure. When the light that's now leaving one edge of the huge LQG finally reaches the other edge, more time will have passed than has elapsed since complex life first crawled across the Earth. For a moment, it held the record cleanly, the biggest thing anyone had ever mapped, and that alone would earn it the #1 spot. But here's the thing. Here's why this one keeps cosmologists up at night. It might not be allowed to exist. There is a foundational assumption underneath nearly all of modern cosmology. It's called the cosmological principle. And it says roughly that the universe is homogeneous. That if you zoom out far enough, to a large enough scale, the universe looks essentially the same everywhere. Smooth. Uniform. No special places. No giant clumps. No enormous structures. Just an even scattering of matter, the same in every direction. Almost everything we believe about the size, age, and fate of the cosmos rests on that assumption being true. And crucially, theory tells us roughly the scale at which the universe should become smooth. The largest structures should top out at a few 100 million light years. Above that, everything should even out into uniformity. The huge LQG is around 10 times larger than that limit. It is a coherent structure, 4 billion light years long, existing at a scale where, according to our foundational assumption, no structure should be able to exist at all. It is too big for the universe to be smooth. If it's real, if those 73 quasars are genuinely one associated structure and not a trick of chance alignment, then the cosmological principle, the bedrock under our entire model of reality, has a crack in it. Now, I have to be fair, because good science demands it. This is contested. Not everyone agrees the huge LQG is a real bound structure. Some researchers have run the numbers and argued that in a universe as vast as ours, random chance will occasionally throw quasars into groupings that look coherent but aren't truly connected, the way you can find a line of trees that looks planted when it's really just random forest. The debate is genuine, and it is ongoing. It may turn out to be a statistical mirage. But sit for a moment in the possibility that it isn't. Sit in the possibility that it's exactly what it appears to be. Because if it is, then it means the universe is not the smooth, uniform, well-behaved place our equations assume. It means that on the largest scales, there are structures so vast they shouldn't be there, lumps and clumps in the fabric of everything, and that our comfortable picture of a tidy, even cosmos is a story we told ourselves because we hadn't yet looked far enough. And that's where I want to leave you, because we started this countdown with a star we couldn't quite measure, and we've ended it with a structure that might mean we don't understand the shape of the universe at all. That's the real vertigo of scale. It was never just about the numbers getting bigger. It's that at every level, from a star with no clear edge to a quasar group that breaks our deepest assumptions, the universe keeps quietly informing us that it is larger, stranger, and less finished than we thought. We build our maps. We draw our limits. And then we point a telescope a little further into the dark, and something is out there that was never supposed to fit on the map. We are very small. We are very new. And we have only just started looking. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.